Welcome to Regents Physics. We're going to begin our discussion with Chapter 1, which is just the science of physics, which is just an introduction to this course. And it's going to be a discussion of a lot of things that you've probably already talked about in other science classes. Other science teachers have already talked to you about it and taught it to you. But again, we need to cover the basics just to make sure they're all dealing with the same thing, all have the same base knowledge. So take notes along with it in your own note packet. We're going to start with Chapter 1, Science of Physics. And just as an introduction, physics is the most basic of all the sciences and considered to be the mother science. Now, some of you may call this the mother and add another word after it. After this class is over, it's a joke. Feel free to laugh. Okay? But for the most part, it is all other foundations of sciences actually derived from physics. Chemistry came from physics. Biology comes from physics. Earth science comes from physics. Astronomy. It is the mother science. Everything comes from there. And basically what physics does is it attempts to explain the world around us. And it's going to be using mathematics. Okay, so this is kind of a key thing. The language of physics is mathematics. You are going to be using a lot of algebra in this class. If algebra isn't something you're currently good at, you will get better at it. There's a tiny amount of trig that we'll have to talk about, but don't worry if you haven't taken trig yet or you're not good at it, we will get better at it as we go. Yep. So we're going to talk about the fact that physics is actually everywhere. And it turns out that you already know a ton of physics without ever having taken this class. You know about gravity and that what goes up must come down. You learned that when you were learning to walk. When you first tottered around from the morning you tipped over and fell over. You learned that the things that go up come down. You know about friction and the fact that if you step on ice, it's slippery, or if you dive on the gym floor, you get that where the skin peels off of your body. You already know a ton about physics already. We're going to be using the scientific method in this class to investigate things. And it turns out that you already know this, you've been taught it before, but it's also something you use every single day to solve your problems. It consists of six different steps. The first thing we'll do is we'll define the problem. We'll do some observation, we'll do some measurement, experimentation, make hypotheses about it, and we'll end up by developing a theory. And we're going to go into this in more detail tomorrow when I have you in class. Okay, but these are the 6 steps that we have to do, and we'll talk about those in more detail a little bit. Now, dimensions. For those of you that have been through chemistry, you know about dimensional analysis. And you're groaning right now, that's okay. Okay? But dimension basically is what kind of physical quantity a number represents. Okay? Because remember, physics is going to use mathematics. So we are going to be dealing with numbers, but we have to know what we're describing. So if I tell you, hey, I've got 5, without a dimension, without a unit, it's basically meaningless. In this class, you're going to be using 7 basic dimensions. We're going to be talking about length, mass, and time. Those are the big 3 we'll use. But then also we're going to talk about temperature, electric current, amount of substance, and light intensity. The amount of substance, the mole, we don't get into a lot, but we will address it a little bit. And everything we're going to talk about this year is either those 7 or a combination of those 7. Okay? This is something, in our classes, we use the SI standard of measurement. We don't use our basic United States measurements. We don't use feet. We don't use miles. We don't use pounds. We're going to use the SI standard of measurement. And that's, again, so that everybody knows what our base units are. Again, if we talk about 5 something, if you don't, if it's going to be different if it's 5 pounds as opposed to 5 kilograms or 5 newtons. So we're going to use the SI standard of measurement in this class. And this was developed in 1791, again, basically so that everybody knew how big a meter was, how long a second was, how big a kilogram is. And we'll talk about those in here just right now. The meter is what are going to be our SI unit standard of length. Okay, it's originally defined to be 1/10 millionth of a meter, or sorry, 1/10 millionth of the distance from the equator to the pole. And it's defined as something else. We'll talk about that tomorrow. The symbol is a lowercase m. Okay, and one thing you have to know is that 1 meter is approximately 3 feet. And this is going to be important because on the Regents exam, they're going to test your knowledge to have you an idea. Do you have an idea of how big a meter is? And we'll talk about that in greater detail tomorrow. I'll give you a couple examples. The SI unit of mass is the kilogram. And this one's weird because it's the only SI unit that comes with a prefix. And a lot of people like to think, oh, well, it's got to be grams. It's not. It's a kilogram. It was set up a long, long time ago. It's just the way it is. We have to accept it. But the kilogram, its symbol is a kg. And you need to know that 1 kilogram is approximately 2.2 pounds. And again, one of the questions I'd like to ask you is, what's the approximate mass of a high school physics student? And so if you know what you are in pounds, you're going to be able to convert that over into kilograms and get an approximate answer. And the other one we're going to discuss is time. Okay? The SI unit of time is the second. Okay? Its symbol, lowercase s. Okay, originally defined as 1/86,400th of a mean or average solar day. And we'll talk about that. But you're going to hear me say this often, that we live in an MKS world, which stands for meters, kilograms, and seconds. Okay, we want to be in those units as much as possible. Okay, as we said before, we want to know what our numbers represent. We want to know what dimension they are representing. To do that, we use units. All measurements must have a unit after them in order to make them valid. If it's a single dimension, then it's just meters. If it's multiple dimensions, then you get combinations. For example, area, and I'll put this up. Area is equal to the length times the width. And so the units for area, why that would be, hang on, let me change that, meters times meters. So your units are meters squared. If you're talking about speed, okay, and this is down here, I'll show this right here. If you're talking about speed, I'll write it out. That's defined as the length or the distance you've traveled divided by the amount of time that it takes. And so units wise there, units for length are meters, units for time are seconds, and so your units are meters per second. Okay, and I also put up another one up there for force, but we'll talk about that later on. But again, these units let us represent. A meter per second is different than a mile per hour, is different than a kilometer per hour, is different than an angstrom per second. You need to have those base units in order to understand how these things are moving. As we previously discussed, the units are extremely important. One of the things that we will use in this class is called dimensional analysis. This dimensional analysis is basically one rule, and that rule is, let me write this down, is that whatever you do to the numbers, so whatever you do to the numbers, you do the same to the units. And let me scroll back up here. If you look, I talked about how speed was length over time. I'm going to give you that equation. In fact, you're going to have access to a reference table that gives you this equation, that speed is length over time or distance over time. And so if your distance is in kilometers and your time is in hours, and so you want to find your speed, your units of your velocity or your speed will be kilometers divided by hours. If you go 5 kilometers in 10 hours, it would be 5 divided by 10, so you get 0.5 as your numerical answer. Your units, 5 kilometers divided by 10 hours, we give you 0.5 kilometers per hour. So that is what dimensional analysis is. Really, I know in times it can be overblown, it can seem overwhelming and much more complex than that, but that's basically all it's going to be. Now, actually it's all written right here. So I'll even highlight this section because it is the important thing about dimensional analysis. Just do the algebra. Whatever you did the algebra on your numbers is the same algebra you do on your units. Now, prefixes. In physics, we're going to be dealing with very, very big numbers. We're talking about distances between here and the moon, here and Jupiter, here in the next galaxy. Those are immense, huge distances. We're also going to be dealing with a very, very small distance between two neutrons inside the nucleus of an atom. Okay? And because of that, because we don't want to write out all that many zeros either before or after our numbers, we want to have SI prefixes. Okay? And on the front page of your reference table, you'll find all of the common SI prefixes we have to know. And there's some that you already know. You already know that kilo is equal to times 10 to the third, or 1,000. You know that milli is times 10 to the negative third. Okay, and there's some other ones on there. There's micro, there's giga, there's centi, all the ones that are listed there. We'll deal with this tomorrow in a couple sample problems to talk about it as well. All right, accuracy and precision. Turns out that because we are using mathematics, which is perfect, to describe our world around us, which is not perfect, when we do measurements, we can be off a little bit. And the two ways we are off is in accuracy and precision. Accuracy is due to you. If you screw it up, that's you being inaccurate. Precision is due to the instrument that you're using. Okay? So if I'm using a stick this long and say, hey, this is a meter, and I use that stick to measure like the width of the hallway, well, I'm going to be off by a little bit because I don't have anything smaller segments than this stick. That's precision. If you just slap it down and go, it looks approximately that, that's accuracy. And we'll talk about that in more detail tomorrow. Sig figs, significant figures. And if you've taken chemistry, you're probably groaning right now. Oh, I hate sig figs. Yep. It helps us to know how imprecise our measurements and, more importantly, our calculations from those measurements are. Okay? And so what we have 4 rules that come off of this. But here's the good news. In this class, sig figs are not crucial. Now, that's not to say that they're not. If you're going to be doing research, if you are going to be working for NASA at some point in time, you're going to want to know about these. Okay, we'll talk about an example tomorrow where somebody didn't do sig figs right and it cost a $6 billion mistake. Okay? But for our purposes, you are going to use common sense. If all of your numbers have 2 decimal places, keep your answer to 2 decimal places. That's just probably the best way to think about it. Okay? So the last thing in here in chapter 1 is as we've stated over and over again, physics uses mathematics. And you've used tables before, you used graphs before, you've used equations, and we will primarily focus on doing equations and algebra from it. A big push is going to be looking at trends, and trends you get from using graphs. Okay? And we're going to be investigating the relationship between graphs and equations. There are 4 or 5 major relationships you have to know. The first one is called direct, and that is as one goes up, the other one goes up by the same amount. And generally, that can be labeled by the equation y equals x. The next one is an exponential. So as one goes up, if one doubles, the other one will quadruple. And generally, it'll be to the power of 2 in here. You could have a power to 3, power to 4, but generally in here, it's always going to be a quadratic. And so as one doubles, the other one will quadruple. The next 2 are almost inseparable, and you are not going to have to know the difference between these 2 or be able to distinguish between these 2. But the first one here, and I'll put it up top in purple, this is an inverse. So if I double one, the other one goes to half. The other one, actually here, let me circle that. That is this one right here. The other one is an inverse squared, and I'll put that in green. So if I double one, the other one goes to a quarter. I'll circle that and circle that. You aren't going to have to distinguish. If you were just to look at these 2 graphs, you're not going to have to know the difference if it's inverse or inverse squared. Okay? But they will ask you the difference between the 2. Negative direct. Now I have to highlight because I couldn't find just a negative direct graph. Yep. The negative direct part is this right here. That's the part. So as one goes up by 3, the other one goes down by 3. So that's what that means. And that's like y equals a negative x. Okay, and the last one you have to know is a constant or no relationship. So y is equal to a constant. So you can do whatever you want to the other one, and it doesn't change that one value. All right, so this is kind of all the stuff you have to know for the beginning stuff. Okay? When we come into class tomorrow, we will discuss a lot of this. We'll expound on a few more details, and then we'll do some sample problems with the dimensional analysis and the graphing and that kind of thing. So everybody have a great night. We'll talk to you later. Bye.